Right now, about 85% of our commercial energy comes from fossil fuels. There's really no good substitute for that source of energy to bring it down to levels where their greenhouse gas emissions will be where we want them to be in order to stop any significant climate change. Therefore, we need to have technologies that will allow us to continue the use of these for a transitional period while alternatives are developed to both provide our energy supply and yet do it at a much reduced level of greenhouse gas emissions.
That's an interesting question because undoubtedly that fossil fuels will continue to be used worldwide, certainly for decades to come yet, in particular in the developing countries. So if we believe in meeting the CO2 reduction targets out in 2050, which are sort of politically being accepted, then there's going to be a huge transition from a position now to where we want to be in 2050. Fossil fuels will be used, therefore the only way to address the clean use in the sense of low carbon of fossil fuels is to use carbon capture and storage, certainly for a large static plant, not just power stations but industrial sites too. So it's an absolutely essential part of the portfolio for meeting these targets.
The capture and storage of carbon in the form of carbon dioxide is basically the byproduct of the combustion of fossil fuels. And as most folks are aware, the increase in CO2 in the atmosphere since pre-industrial times has been well documented. This increase in CO2 has been related through modeling to increases in global average temperature. So the idea of avoiding CO2 emissions to the atmosphere is a way to potentially mitigate the continuation or even the more extreme climate change effects that might be forthcoming in the future.
Well, mainly as a way to mitigate CO2 emissions to address the global climate change concerns. We all know that despite the difficulties in producing oil and gas and coal as fossil fuels, we are going to be dependent on them for a foreseeable future. So in order to be able to use them safely, and despite the concerns about the CO2 emissions and climate change, it's important that we have technologies both to increase efficiency, but also to reduce emissions by technologies like carbon capture and storage. And if we can show that this carbon capture and storage technology can work effectively and safely at large scales, it will provide a bridge and time period over which other options for energy can be developed, and while we still have reliance on the fossil fuel for the next few decades at least.
Climate change is a major issue. We believe, scientists believe, that climate change is being accelerated by what's called anthropogenic or human-sourced emissions of carbon dioxide in the atmosphere. That's causing carbon dioxide levels in the atmosphere to increase at rates that we believe are unacceptable for long term. And in order to deal with these human emissions of carbon dioxide into the atmosphere, a variety of techniques we think are needed to reduce the CO2 that results when we burn fossil fuels. And one of those techniques that we believe is very important is to capture the emissions of carbon dioxide that are being emitted from things like coal-fired power plants, cement plants, refineries, ethanol plants even, and other stationary sources especially, is to employ what's called capture and geologic storage. In other words, separate the CO2 from the gases that come out of these plants, compress it and inject it into deep underground formations and store it essentially permanently to keep it from getting into the atmosphere. It's not the only thing that we have to do. We have to do conservation, renewables, and others as well to reduce the amount of fossil fuels that we burn. But we feel that we've got to figure out a way to capture these emissions and store them as a key part of an overall strategy. Otherwise, it's going to be extremely expensive to deal with climate change, we believe.
Climate change is an enormous challenge to all of mankind. And we need to employ all technologies in order to reduce the amount of CO2 that's going into the atmosphere. We need to look at using renewables, wind, solar, improving efficiency, but we also need to look at carbon capture and storage as part of the portfolio to meet this enormous challenge of reducing the amount of CO2 going into the atmosphere. And so as part of this portfolio, it's a technology which has its basis in a very long history of technologies, and so it's one that we can readily apply to this huge problem of trying to reduce emissions into the atmosphere.
We should capture and store carbon to allow us to accomplish a couple of things. First of all, as we look at the world and the concern about increased global warming and a larger carbon footprint, it provides an opportunity to remove carbon from our most abundant fuel, our hydrocarbons. That process not only allows us to maintain our existing power plant fleet and industrial fleet that depends on coal, but it ensures the long-term capability of being able to mine the coal, these 250 or more years of coal that we have in reserves, and to continue to use hydrocarbons as we go through a transition that gets us to other fuels in the future.
We pump lots of fluids in the underground, including CO2. We put maybe 30 million tons of CO2 in the ground a year for enhanced oil recovery. The type of reservoirs we were talking about putting CO2 in are not that much different than the oil reservoirs that we're pumping in today. So therefore we know we can do it. The big issue there is, of course, is the underground is very heterogeneous, meaning that no two reservoirs are exactly alike. So we need to understand each reservoir as we pump it in. But there's no doubt we can pump it in. Exactly how much we can pump in each reservoir we'll understand better with experience. But right now it looks like we have plenty of storage space from all the potential reservoirs that are out there.
Funny that you ask about CO2 storage. Is that a myth or reality? I actually have a Google YouTube presentation with that title exactly. So certainly we can store carbon dioxide underground. We know that because there are natural analogs, both in oil reservoirs, gas reservoirs, and CO2 reservoirs. And we have many decades of experience with CO2 enhanced oil recovery, and we have 4 projects in operation today that are specifically intended to capture and sequester CO2 that are all working quite well.
No, it's not a myth, certainly. It's being done around the world at various sites around, certainly at the size of 1 million tons of CO2 per year. So it's certainly not a myth. It can be done. And the monitoring of these demonstration sites, which are all over the world. They're in North America, in Algeria, in the North Sea, in Europe. These are being done and they're being monitored accordingly. So it's not a myth at all. You can do it.
Carbon sequestration is very much a fact. There's still some things that we need to prove about the sequestration, which unfortunately, the nature of chemistry, it's going to take a long time to prove. But we'll go ahead with sequestration because we're confident the chemistry will work. I mean, there's no question that we've been putting things in the ground for many years. And sequestration, as we're doing it now, both with the DOE program and other places like in Sala and the Schleppner Fault, I mean, the CO2 is staying where it's going. We're doing it today. We're involved with it at American Electric Power Mountaineer. And the whole issue is to get it down and get it in the aquifer, and eventually it will become carbonates. And that's the long-term prognosis, but that's the part we can't prove. But there's no question that the technology that surrounds it is sound.
I think where we are is at the point of moving CO2 sequestration, storage, and capture in the underground to reality. And in order to accomplish that, we are carrying out a large number of tests at various scales to inform us on our ability to actually make it a reality. But the expectation is, based on the work that we typically do in oil and gas reservoirs, the fact that we store enormous quantities of natural gas to facilitate consumption in cold climates during the winter, all of those are positive indications that we can move this toward reality in the future.
Underground CO2 storage is a reality because it's been shown that you can inject CO2 in the ground. So there are two parts to this question. One is, can you inject CO2 into the deep geologic formations? It's been shown again and again that even with a single well, for example, you can get rates up to 1 million tons per year. So injection of CO2 is a reality. Can you store it safely? That is also correct, as long as you're taking all the safety precautions that you need and you're doing proper site evaluation. So that is also a reality, but you have to make sure that if you're doing it at large scale, you do the proper risk assessment, site characterization, and monitoring so that you are not creating unacceptable risks for current or future generations.
It's a reality. It's already being done at several sites around the world, Schleipner, Insala, Weyburn. There's an active enhanced oil recovery industry that's been around for decades that exists in this country, primarily in the Gulf Coast area, but not entirely just the Gulf Coast, where CO2 is pumped underground and used to stimulate the production of more oil. And in the process, some of that CO2 ends up being stored underground. And of course, CO2 occurs naturally underground in various places like Jackson Dome, for instance. And it's been demonstrated through those natural processes that it can be stored for millions of years in these underground formations. So in that sense, it is being done. It's being both done by humans, but it's also been done by nature. And certainly in a properly designed and engineered system has been shown that it can work.
So when we think of CCS, we think, generally speaking, of capturing CO2 at large sources like power plants or industrial facilities. And in fact, I want to point out that this technology is not just about capturing CO2 from coal burning power plants. It's about capturing CO2 from any large source of CO2, such as refineries, cement plants, natural gas-fired power plants, as well as coal-fired plants. And then what do we do with all of this CO2? We have to transport it to locations and pump it into the deep subsurface. The concept of working in the deep subsurface is not new. This is not a new, novel idea of injecting things into the subsurface. There's been decades of industrial experience which forms the basis on which we can move forward with this technology. And one of the ones that people are most familiar with is natural gas storage. We have many natural gas storage fields across the United States, and these are essentially injection operations where natural gas is injected into the subsurface, stored over time, and then withdrawn when people need it. Well, what are we going to do with in sequestration? Is we're simply going to inject a different kind of gas, CO2, which is even less dangerous than methane, if you will, into the deep subsurface and store it over long periods of time. So this is by no means a novel thing that has never been done before, and from that standpoint, you know, it's an important thing to think about, in that we have learned a great deal from this historical experience.
There is some underground CO2 storage going on today in various forms. You know, in this country and elsewhere, we've used CO2 in enhanced oil recovery, and we have in fact injected large quantities into depleting or depleted oil fields. The intent of that work has not been sequestration per se, but what's clear from the data is that a certain percentage of the CO2 does remain after injection, remains in the ground. Now, other attempts to more consciously do sequestration are, I would say, in their infancy. We are currently doing a project at one of our power plant sites in northern Kentucky, our East Bend site, where we've injected several thousand tons of CO2 deep into a saline aquifer, and we're monitoring that material to see how it migrates and how it, how it changes chemical form, how it creates carbonates, and really what the life of that material looks like post-injection. A number of others are doing similar work that we're aware of. So I would say, when you ask the question, I believe the form of your question was, is it possible, right? Or does it work? Myth or reality? Yeah, myth or reality. I would say it's a reality. What we really want to make sure we understand are the full set of dynamics around that reality. Is it, how does it really behave? How much does it cost? What happens to the material in situ over long periods of time?
So the question is about, can CO2 storage be safe? And certainly it can. We know that from the projects that are ongoing today. One needs to be careful and select a good site. One needs to monitor. One needs to have regulations to make sure that all of those things are done. But certainly CO2 sequestration can be done safely today.
I think all indications right now are that storing CO2 underground is safe. It doesn't mean that there will never be a leak, but even if there is a leak, CO2 is not a toxic gas, it's not explosive. Right now we put it in the atmosphere out of smokestacks of chimneys, out of our tailpipes of automobiles. So, if some escapes, it's generally not a health hazard. It's only a health hazard if it escapes in very concentrated forms. But because of putting it into the ground, it usually will not come out very quickly. You can sort of think if CO2 escapes, it's not escaping from, say, if you put water in a water balloon and puncture it, everything comes out. But it's more like putting water in a sponge. The water doesn't want to come out that easily, and you have to really wring it tight to get it out. So putting CO2 in the ground is more like putting water in a sponge, and it's not going to want to come out in the types of volumes and flow rates that would be necessary to make it a hazard.
Yes, provided you characterize where you're going to store it, and that's the issue. With the appropriate characterization and understanding of where you're putting it, then yes, it is safe.
Absolutely. I mean, it's really simple. There's CO2 stored in the earth for millions of years. It's there right now. And, occasionally some CO2 obviously comes up, and that's, the geysers are nothing but CO2 and hot water. So there's obviously natural emissions of CO2. But there's large deposits, just like there's large deposits of, natural gas. Well, when you take natural gas out of the ground, it's usually 35% or so CO2. So, I mean, this has been stored down there for millenniums, literally. So we know you can store things in the earth and that they'll stay where you put them.
Well, that's again one of the questions we're moving toward a better understanding of. We want to ensure that the CO2 does not leak into groundwater resources, that it does not pose a health and safety risk. And by doing the experiments which the Department of Energy has funded, I think we're going to be in a much better position to understand that question of safety. Right now, because CO2 is not flammable, it's not hazardous in small concentrations, I believe that these tests will result in an outcome and a verdict of it being quite safe.
We certainly believe that it can be safe, that it can be a relatively low-risk endeavor in a properly selected and designed and operated storage site. And again, the way we come to that conclusion is by looking at both the history of humans doing that through some of these large projects that have been going on for many years, and through the EOR experiences or the enhanced oil recovery experiences, but also looking at natural analogs like naturally occurring CO2 deposits underground, and looking at the geology and the characteristics that have made those secure sites for literally millions of years. So yeah, I think the answer would be that we believe it can be safe, but we need to have the right knowledge to make sure that we design it properly, implement it properly, and operate it properly.
geologic storage is a technology which is safe. I would have no problem in having my house on top of one of these storage projects. And why do I say it's safe? In part because it is built upon the technological experience that I've described. And so through decades of working in the subsurface, we in fact have learned about the hazards and risks associated with working in the subsurface. And now we can apply that knowledge to this technology. And there's another important issue. People worry a lot about leakage associated with CO2. Will it come back to the surface? And nature has provided the fundamental evidence to tell us that we can in fact safely store CO2 such that it won't come back to the subsurface. And that evidence is the oil and gas reservoirs which we find throughout the world. Those reservoirs contain fluids which are lighter than water, just like CO2, and hence also tend to want to come back to the surface, just like CO2 would. But nature has provided the geologic structures and the properties of those structures to keep those fluids in the subsurface for millions of years. So we know that there exist geologic structures which will safely store CO2 for millions of years, simply from the observations we have of oil and gas reservoirs.
I certainly believe it could be. And once again, it depends, I think, significantly on the nature of the geology that you use for sequestration or the nature of the process that you use. A number of folks are working on technologies with, I think, at least the potential to utilize CO2, sequester CO2 in useful products such as cement and aggregate. So more work to be done in my mind in terms of making certain that if what we're talking about is terrestrial sequestration, that we understand the geology very well, that we pick geologies that are well suited, and that we monitor them well. If it's materials such as cement and aggregate or other kind of secondary use materials, we need to understand what happens to those materials over time as well.
Right now in the U.S. we have a couple thousand miles of CO2 pipelines. They've been tracking any problems with them. There's been no real significant accidents in terms of, say, loss of life or anything close to that. Has a much better safety record than natural gas. Once again, CO2 is non-toxic. It's non-flammable, so unlike other types of pipelines that have flammable gas like natural gas, which may explode if you have pipeline leaks, here that will not happen. They have lots of safety mechanisms in there, so if there is a leak, the pipes will they'll have shut-off valves, so not a lot will escape, meaning it's really not much of a hazard. So between the good safety record that we've seen so far and the sort of benign nature of CO2, I think it's very safe and effective for transport.
So today we have many hundreds of thousands of miles of natural gas pipelines. Transporting carbon dioxide is much the same as transporting natural gas, and in fact in the United States we have more than 2,000 miles of pipelines that transport carbon dioxide safely. So yes, this too can be done safely.
Yeah, I think it is, because to my knowledge there's at least 30-40 years of experience of moving CO2 around in pipelines, certainly here in the US. That's the case, natural CO2, but going down to be used in enhanced oil recovery in Texas. So I would have great confidence that of the ability to move CO2 around in pipelines in a safe manner.
Absolutely. Generally, when we talk about transportation of carbon, we're talking about a pipeline. There's, I believe, 6,000 miles of CO2 pipeline already in the United States alone. There's CO2 going through those pipes every day. has been for many years. It's not something that people knew about until, frankly, all of this suddenly became a major point of interest. But there are processes that have been using CO2 for a very long time, and that's how it's transmitted around Texas. It's taken up into Canada. There's, it's just basically pipeline transportation. And technology is no different than moving natural gas through a pipeline or anything else we move through pipelines every day.
Well, we've been moving CO2 in West Texas for enhanced oil recovery projects since the early 1980s, so there's more than 30 years of experience there. There's never been a fatality, as far as I know, in relationship to that pipeline operation. So we move CO2 hundreds of miles from source wells in Colorado and New Mexico into West Texas. Those pipeline systems have been working safely, as I said, for some 30 years or more. So the transportation of a non-flammable, non-explosive gas would seem to be readily accomplished, especially compared to the fact that we have hundreds of thousands of miles of natural gas pipelines in this country, which are operated by and large in a relatively safe mode.
The answer would be yes. When properly designed and implemented, it certainly can and should be. And partly a way we come by that conclusion is again to look at a historical experience. There is an active CO2 transportation system using supercritical CO2 in pipelines that's been around in this country for, again, decades, servicing the enhanced oil recovery business primarily out west. There's several thousand miles of high-pressure CO2 pipeline that have been operating again for a number of years safely. And then you also have the natural gas pipeline system in this country and elsewhere around the world where it's been demonstrated for many decades that, again, with proper design and attention to operational characteristics, et cetera, that gases like natural gas, which is of course quite different than CO2, but also CO2 in supercritical form can be transported over long distances in huge volumes at very high pressures with a very, very good safety record.
Since the 1970s, there's been active use of CO2 for enhanced oil recovery, and particularly in Texas and in other areas. And because of that, the CO2 transportation technology was developed and tested over periods of time. And so today, this is considered standard technology for transporting CO2. And people understand that there's certain things that we need to do to keep the CO2 dry, for example, so it doesn't corrode the metals in the pipelines. CO2 is transported under pressure, but we've had decades of experience in transporting fluids in the subsurface under pressure, and people understand how to control it. It's worth noting that CO2, even though it's under pressure, if it was released, it would not have an explosion. It would not burn as people envision natural gas doing. It just doesn't do that. So it's in fact a safer kind of transport than we're used to dealing with in the natural gas industry.
CO2 transportation is safe and reliable. It's a proven technology. We have had CO2 enhanced oil recovery practices going on in the Permian Basin for some 30 years. Those pipeline networks are in place. They've been operated successfully and safely and have an excellent track record.
CO2 capture is a proven commercial technology. It's in place at maybe a dozen or so power plants around the world right now, as well as in many industrial processes. It's used to make CO2 for commercial products. The big difference between where we are in CO2 capture today and where we need to get to is the scale. So most of these plants are a few hundred tons a day, or maybe even up to 1,000 tons a day. But a 500 megawatt power plant, if we want to capture the CO2 out of that, is at 10,000 tons a day. So there's some scale up issues, but nothing is It's really a matter of experience and development. There's no fundamental issues that we can't get up to that scale.
Capture of CO2 certainly does work. It's been used again for many years. Perhaps not at the scale that we're talking about now, that we need to do now to meet the CO2 reduction targets in 2050, which are politically being accepted now. So it's not been done at the scale that's necessary, but certainly there are many technologies, mostly back-end cleanup or post-combustion technologies that are well proven, in my view.
Well, certainly CO2 capture works. CO2 capture is a process that already is underway at refineries, and CO2 capture is used to produce the CO2 that we have in soft drinks and dry ice and other industrial uses of CO2. So capturing the CO2 is a known process. The question is whether we can expand it at scale to deal with the large quantities of CO2 that are emitted from power plants, such as those, for example, from coal-fired power plants.
CO2 capture does work because the processes and the fundamental chemical processes that are used for CO2 capture that have been shown to work at least small scale. And as we know that there are many CO2 capture facilities with processes like amine capture, Selexol capture, that can capture CO2 from both low purity and high purity CO2 streams. The big challenge that we have coming up is the scale up issues. And how do we, if we have to deploy CCS at a large number of facilities at full scale power plants, you are going to need ways to reduce the energy penalty and the cost, and also look at how do you integrate it with the overall energy infrastructure. So those are the technologies and options that are being looked at, and to see if there are cheaper, better, and more integrated ways for CO2 capture.
Yes, there are CO2 capture processes that are out there every day capturing CO2 from gas streams and producing a pure stream of CO2 that can in fact be injected into deep geologic formations. And in fact, one of our test sites in the Midwest Partnership has demonstrated that. At our Michigan site, CO2 is captured from a natural gas stream, in this case, at a concentration that's not too different than what one would find in a coal-fired power plant exhaust stream, roughly 10 to 20% CO2. But their amine systems have been used for a long time to separate that CO2 out and put it in a form that we've demonstrated can be injected into deep geologic formations in that area. And we've injected over about 60,000 tons of CO2 in that way to date. So it can be done. It's expensive and it's energy intensive to do that. And to employ that technology at a scale appropriate for large coal-fired power plants has significant economic and energy penalty challenges associated with that. So there's a lot of interest and a lot going on to develop other capture technologies or processes that can do that job at much less cost penalty.
So capture of CO2 is actually a really well-known process. It's been underway for decades in various industries across the world. And one of those industries, for example, is the gas separations industry, where methane and other valuable gases extracted from the subsurface may have CO2 in them, and they are the CO2 is removed and from those gases through standard processes. These processes currently are primarily chemically based processes, and they do add quite a lot of costs to the whole technology of CCS. But it's one of these areas where there's an enormous amount of work going on now to look at new technologies for reducing those costs, and those costs will definitely come down as time goes on and new advances are made with regards to the separations technology that we need for capture.
It appears to. I have now been to a couple of places, a couple of plants, both domestically and internationally, where CO2 capture is taking place on a pilot scale. And so I can say, yes, I've seen it and it works. Now, the other part of that question is, does it work? How economical is it? And I think that's an area yet to be improved, both in terms of the amount of energy it takes to do capture and just the sheer cost of capture.
CO2 capture works. The technology that is used to capture the CO2, separate it from other gases, and compress it so that it can be transported to sequestration sites is a series of technologies that already exist. The challenge we're faced with is to scale up those technologies and to integrate the technology. So we feel very confident that we have the technology. It's a matter of applying the existing technology to new scenarios, and also there's a challenge as we integrate that to also reduce the cost of capture. But certainly it is a feasible technology.